Okay, let me start. Today we're going to talk about the eigenvectors and eigenvalues. So this is the starting of the lecture 13. So let's start. So before starting, we have a very important notification about the final exam. So we will take a offline final exam. So please remember that because uh, I think we can do the final exam with the online, but there might be some problem, something like the cheating. So we decide to do the offline final exam. So please remember this one. So the date will be the June 23 from 5 p.m. to 6:30, and the location will be announced soon because the in this semester there are so many unexpected situations, so we have to organize the room to do the final exam. In our case, we have the 10 students, so we might need the two more rooms to the room for the final exam. So we will organize. We are now organizing this one, so we will announce the location soon, and the scope of this final exam will be the from lecture 1 through the lecture 13. So it might be the entire part, entire lectures. So now we have lecture 13. So yeah, we are almost done. So no books, no calculator or other electronic device, something like the smartphone, are not allowed. So please remember this one. And I strongly suggest you, please start your study or please start your learning now, because uh, because in this semester we didn't have the midterm exam, right? So the scope of this exam will be really huge. So I strongly suggest you start your study now. Okay, so it was the notification. Today we're going to start the eigenvector decomposition and eigenvectors and eigenvalues, right? So before starting, I want to make up the property of the determinant in lecture 8.2. Actually, this kind of the determinant concept will be used in the next lecture in the eigenvalue properties of eigenvalue decomposition. So I want to recap the properties of the determinant. So as you know, if we have the matrix A and B in n by n n by whose size n by n, then there are several kinds of the properties, right? First one is matrix A is invertible if and only if the determinant A is not zero. It was the first property. And second property is that the determinant of the A times B is equal to determinant of A times determinant of B, right? And another one is that if the A is the triangular, then determinant A is the product of the entries on the main diagonal of the A matrix. Okay, so actually in the lecture 8.2 we already talk about these three kinds of the property, but we skipped this property. So today we will just briefly prove this property. So in here, determinant A transpose should be equal to determinant of A. Okay, so how can we prove this one? So actually, to prove this one, we need some kind of the principle of the mathematical induction. So here's the proof this one. So okay, so when we say the n is equal to 1, the matrix A is just a scalar value, right? So in this case, determinant A transpose determinant A is always true, right? So because A and A transpose is just a scalar value, right? And then when you think about when you think about okay, let's use this color. Yeah. Okay, so let's say the n is the k plus 1, and this here this property is true when k by k matrix. Okay, so in this case the cofactor of the so a k plus 1 and k plus 1 and a transpose the k plus 1 and k plus 1, right? So to estimate the determinant of this A and A transpose, we can use the compact expansion method, right? Started in the lecture 8.1 and 8.2, right? So what was that? So if we think about the cofactor of this law, then the determinant of this one will be used, right? In other words, we can use another column, then remaining part in the matrix will be used to estimate the determinant of the determinant of the A transpose, right? So we already know this one and true, right? Because the A transpose is just the swap of the row and columns, right? So this theorem, in this case, this is also true, right? So when n is equal to 2, k will be the 1, right? So we already know the 1 by 1 case, this property is true, right? So we can say that by mathematical induction, this theorem is true when n is equal to n is larger than 0, larger than 1. Okay, so this is the proof of this property. Okay, so today we are going to move the eigenvectors, eigenvalues. So these eigenvectors, eigenvalues are one of the most important concepts of the linear algebra. Actually, this part or this lecture is why we studied the linear algebra. So this eigenvectors and eigenvalues concept popularly used in many applications, such as the economics or the physics, something like this. In our computer science department, this kind of concept are also widely used in many applications. For example, in the machine learning or deep learning, so we can use this kind of concept to understand the transformation between input and output. Okay, so let me start the what eigenvectors, eigenvalues mean. So before starting, I want to recap. I want to explain the meaning of the eigen here. So what is the meaning of the eigen? Actually, the prefix eigen is adopted from the German word. So the meaning of this eigen in English is something like the proper or characteristic. In Korean, 특징. So it means that by using the eigenvectors and eigenvalue, we want to interpret it, or we want to analyze the linear transformation denoted by matrix A. Okay, so let me show you some figure. So let's think about one linear transformation, right? So from left hand side, so you can see the image that consisting of the two-dimensional space, x1 and x2, right? Then by using the arbitrary matrix transformation A, we can transform this image or this signal to something like this, right? So, for example, this output will be generated by the shear transform. We already discussed this one. Okay, discussed this one in the previous lecture, right? Matrix operation lecture, right? Anyway, so as you can see here, this vector moved to this one, right? With the different lengths, right? By the way, but when you see this vector still remain here, right? And fixed here. So this vector has the same length, same direction and same length before and after multiplication, right? So in other words, actually there are so many vectors in the input space, but this vector only determine the characteristic of this transformation. Why? Because we can understand. Okay, this vector will remain after multiplication, and the length of the vector after multiplication will be blah blah. Then we can understand this matrix matrix A or the transformation A can make output space something like this, right? So that's why we study the eigenvectors and eigenvalues. So here is another example. Okay, so when you think about the input space, something like this, right? And by multiplying some kind of matrix A, let me say the shape of the output is something like this, right? But if we know this vector only change the length with the same direction, right? Something like this, right? So as you can see here, right? This vector v1 and v2 will have the same direction with the different magnitude, something like this, right? So in other words, if we know this vector and this magnitude, then we can understand the properties of this transformation A, right? So by using this eigenvectors, we can understand this matrix, right? So that's why we study the eigenvectors, eigenvalues. Okay, so let me show some technical definition. So here's the technical definition. So eigenvector of the n by m matrix A is a non-zero vector x such that ax is equal to lambda x. Okay, so in other words, in this case, here is the v1. So actually, this one should be A transpose v1, right? Because we multiply v1 with the matrix A, right? But we can find out this lambda 1 that satisfies this one. So in other words, to find out the v1 and lambda 1, we can set the new equation, something like this. Okay, let's use the different stiffness. A V equal to lambda V. Okay, so by finding the V and lambda, we can understand the property of the matrix. So in this case, this matrix V is called the eigenvector, and this lambda is called the eigenvalues. Okay, so technically, that is the eigenvector is the non-zero vector that satisfy this equation. And the scalar lambda is called the eigenvalue of matrix A if there is a non-trivial solution of X that satisfy this equation. So non-trivial solution means X shouldn't be the zero value anymore, so X vector will be the non-zero vector here, right? So if there is some kind of the vector X with the scalar value lambda that's satisfying this one, then we can say that this is the eigenvector and eigenvalue, and such an vector X is called the eigenvector corresponding to the lambda. Okay, so this is the definition of the eigenvectors, eigenvalue, right? Actually, this is the one of the important pages in today's lecture. Actually, if you properly understand this one, in the remaining part is just calculation. So if you understand this one, we can just find out the eigenvectors, eigenvalue that satisfy this equation. Okay, so it's really easy. So please try to understand the meaning of the eigenvectors, eigenvalues from this slide to this slide. Okay. Okay, so let's think about how to find out the eigenvectors, eigenvalue. Okay, so before starting, in here I said the lambda is the eigenvalues of the n by n matrix A. So how can I find this one? By using this equation, we can make another equation something like this: A minus lambda identity matrix times vector X is equal to zero vector, right? So in this case, two existed eigenvalues, eigenvector. This equation has a no non-trivial solution, right? If this equation has only trivial solution, as X is equal to 0, right? Then in this case, there is no eigenvalue. Eigenvalues, eigenvector, because it was the definition here, right? Non-zero vectors, right? And the set of the whole solution, okay, let's say this is equation 1. Set of the whole solution, including the zero vector and the non-zero vector, because this is the homogeneous system, right? So because this is homogeneous system, there will be the two kinds of possibility, right? So the trivial solution case and non-trivial solution case. So if there are non-trivial solutions, but the set of the whole solution of this one is just a null space of the matrix, this one, right? So it will be the another matrix A prime. So something like this. So in this case, A prime X is equal to 0. So this is a homogeneous system. So the set X that satisfies this matrix is called the null space, right? So we already know when the null space is defined Rn space, this is a subspace, right? So in this case, this null space is called the eigenspace of the matrix A corresponding to the lambda. Okay. So in other words, so the set of the eigenvectors that satisfy this equation is called the eigenspace. Okay. So in other words, eigenspace consisting of the zero vector and all the eigenvectors, right? why there is a zero vector in the eigenspace? Because this is a null space. This is the homogeneous system, so it always has the zero vector as a solution. So the eigenspace consists of the zero vectors and all the eigenvectors. Okay, so this is a property. Okay, let me show you some example. Okay, show that the 7 is the eigenvalues of the matrix A, something like this. Then the question was find the corresponding eigenvector. Okay, so let's do that. First of all, the scalar 7 is the eigenvalues of A if and only if the equation AX equals B, AX equals the 7X has a non-trivial solution. Okay, so it means that this equation is equivalent to this equation, right? So in other words, something like this, right? So the question is to check there is the non-trivial solution or not. So we already do this in the definition of the null space, right? Okay, so let's do that. So to solve this equation, we can make the matrix form, right? So okay, so matrix A is here, and 7 identity matrix I is here. In this case, identity matrix will be the 2 by 2, right? Because the size of the matrix A is 2 by 2, right? So what was the matrix A? 1652, and the 7 identity will be the 7007. Okay, so finally it will be something like this. And from here, there exists the two column vectors, right? The columns of this A minus 7i are obviously linearly dependent. Why? Okay, let's say this is the A1 and A2, and we can easily show that A1 plus A2 is equal to zero vector. So in other words, there exists the non-zero values as a 1 and 1. So we can say that these equations are these matrices are linear columns of this matrix are linearly dependent. So it has a non-trivial solution. So if we go back to our previous lectures, if the column vectors are linearly independent, there is only trivial solution as x equals 0, right? You understand what I mean? So I show that, okay, C1 x1 plus C2 x2 through the Cn xn. Okay, let's think about this equation. So if this this vector x1 through the xn is linearly dependent, let me say, if the x1 and x1 through the xn are linearly independent, there is only trivial solution as a x okay. Okay, C1, C2, Cn is equal to 0, right? So if these vectors are linearly dependent, then C1 might not be the 0. Okay, so this is a linearly dependent and linearly independent in the homogeneous solution, right? Okay, so in this case, to find the corresponding eigenvectors, we can use the row operation, right? So by using the row, elementary row operations, right? So how can we do that? Okay, so first of all, we can remove this one by using this one, right? So okay, so and then we can normalize by -6 on first row, right? So we can do that, but after that, we can get the echelon form of the matrix A, something like this, right? So in this case, there's only one pure position here. So we can say that there is the non-trivial solution. And how? Because when we represent this matrix as a equation, so it will be x1 minus x2 is equal to 0. Yeah, that's it, because there's no equation here. So in finally the solution, the vector x can be represented x1 and x2. So it will be the negative x2 plus x2 x2. So it will be the x2 with the 1 by 1 vector, right? Something like this, right? So the general solution of this equation is x2 1 comma 1. So the each vector of this form when x2 is not equal to 0 is the eigenvectors corresponding to lambda. Lambda is equal to 7. So for example, when x2 is equal to 1, the eigenvector will be the 1 comma 1, or the when x2 is equal to 2, it will be 2 comma 2, or the 0.5 comma 0.5, something like this, right? So it will be the eigenvectors of the this equation, this matrix. Okay, so it's very easy, and we can solve the more higher dimensional matrix by using the similar formulation, right? Okay, let's say the matrix A is something like this, and we want to find out the eigenvalues of the matrix A, but we already know eigenvalues of the matrix A is 2. In the later, we will talk about how to find out the eigenvalues, but in here, let's assume that we already know the eigenvalue. Then the question is, find the basis for the corresponding eigenspace. What was the eigenspace? Eigenspace, the set of the whole possible eigenvectors, right? So, okay, let's do that. So first of all, to find out the eigenvectors, we can use this formulation, right? Then, okay, so here is the matrix A. Then here is the 2 times identity, right? So yeah, it was the 0, right? Then by subtracting these two matrices, then we can get 2, 2, 2, negative 1, negative 1, negative 1, 6, 6, 6, right? So this is a minus 2i, and we can row reduce this augmented matrix for the a minus 2ix is equal to 0 to find out this vector, right? Okay, so let's do that. So from this matrix, from this matrix, this is augmented matrix. Then how can we do that? Okay, we can easily eliminate these two terms by multiplying the negative 1 on the row 1, and then adding those kinds of output to this row 2 and row 3. So it will generate the 0 and 0 here, but interestingly, this term also remove this term and this term. This one also remove this term and this term. So there will be the 0, 0, 0, 0 here. Okay, so it's very interesting. So in this echelon form of the augmented matrix, there is only one pivot position here. So when you think about x1, x2, and x3, there is this x2 and x3 is a free variable, right? And this x1 is the only basic variable, right? Then we can represent the solution vector x as a vector x in terms of the x2 and x3, right? How? Okay, from this first law, we can find out the one equation as x2 plus 6x3 is equal to 0, right? So x1 is equal to 1 over 2x2 plus minus 3x3, right? So x1. So in here, okay, so we can represent the solution vector x as a x1, x2, and x3 on each element, and from this one we can represent x2 with the 1 over 2, 1 and 0 vector, plus x3 with negative 3, 0, 1 vector here, when x2 and x3 are free variable. So it means that by choosing any arbitrary values of the x2 and x3, we can generate the infinitely many eigenvectors, something like this, right? So interestingly, okay, so let's think about the vectors, something like this, that generate with this equation. So it will be every possible vector x will be the eigenvectors, right? And this kind of eigenvector build the eigenspace when the lambda is 2 from here. So as we discussed previously, by multiplying matrix A on this eigenvector, the direction of the eigenvector would not be changed, but the length of this eigenvector is only changed. So in this case, this length is determined by lambda. Lambda was 2, right? So in this case, this vector will be the same direction with the 2 times magnitude here. In this case, 2 times larger than this one, right? So this is the eigenspace after transformation by matrix A. So this is very interesting, right? So as you can see here, if we considering the eigenspace in the input domain and output domain, the eigenspace still same, right? Only difference is that they are built with the scalar times, right? So without this one, actually this eigenspace will be the exactly same from input and output space, right? So and then this eigenspace is determined by basis vectors, right? So in this case, this one and this one is basis function. So in this case, the eigenspace, the basis for the eigenspace is something like this. Okay, so this is the eigenvectors, eigenvalues, right? Okay, so here is the theorem. So eigenvalues of the triangular matrix. Until here, we assume that arbitrary matrix A, but when you think about the triangular matrix, something like this, then eigenvalues of the triangular matrix are the entry on each diagonal itself. So this theorem means if the matrix A is a triangular matrix, then eigenvalue should be the main diagonal itself. Okay, so in here we cannot find out the eigenvalues on this matrix A directly, but if the matrix A is the diagonal matrix, triangular matrix, then we can easily find out the eigenvalues, because the entries of this triangular matrix is eigenvalues themselves. Okay. Okay, let's prove this one. So for simplicity, let's consider the 3x3 case. So first of all, to understand the eigenvalues, we can use the where is that? Yeah, this equation, a minus lambda I times vector x is equal to 0. So yeah, let's do that. So this is a matrix A and this is a lambda identity matrix, and by subtracting these two matrices, and we can find out the A11 minus the lambda, A12, A13, A22 minus lambda, A23, A33 minus lambda here, right? So the first of all, the scalar lambda is the eigenvalue of the matrix A. If and only if the equation ax minus lambda I times x equals 0 has a non-trivial solution. So we already know to have the non-trivial solution, the equation has a free variable. Okay, so let's analyze this equation has the free variable or not. Okay, so as you can see here, actually this equation is already echelon form of the matrix, right? So because the shape looks like this, right? Then in this case, x1, x2, x3 values are here. Then if this one will be the pivot position if these values are non-zero. Otherwise these values are 0, then each variable will be the what? Will be the free variable, right? So in other words, because the zero entry in here, it is easy to see it has a free variable if and only if at least one of the entry on the diagonal is 0. So here, right? So if this one is the 0 variable, this one is 0, then we can say the x2 is a free variable, right? This one is 0, then we can say that x3 is the free variable. So in this case, this happens if and only if the lambda is equal to one of the entry A11, A22, A33 in matrix A. So in other words, here A11 minus lambda is 0 when A11 is equal to lambda, or A22 is equal to lambda, or A33 equal to lambda. So in those cases, that satisfy this one, right? So in other words, by just seeing the original matrix A on the diagonal term, we can determine one of these values will be the what? Will be the eigenvalues, right? So this is the one theorem. And yeah, this is the last theorem, but yeah, it might take some time, so let's take some break. Okay, so let me continue. So the vector, okay, here's one more theorem. So let the vector v1 through the vr are eigenvectors that correspond to the distinctive distinct eigenvalues lambda 1 through the lambda r of the n by m matrix A, then the set of these kinds of vectors v1 through the vr are linearly independent. So in other words, the eigenvectors with the different eigenvalues will be the linearly independent each other. Okay, so let's prove this theorem. So first of all, suppose that the v1 through the vr is linearly dependent, right? Then we can show this assumption will fail. So let's do that. So first of all, since the v1 is the non-zero, right? v1 is non-zero. Why? Because v1 is the eigenvector, right? It was the definition. So then one of the vectors in the set is a linear combination of the preceding vector, right? So in other words, okay, let me say there's vector v1, v2, v3, blah blah blah, vp, blah blah blah, vr, like this. Yeah, there are vectors, right? If we assume that it is the linearly independent, then some arbitrary vector vp can be represented by the linear combination of this one, right? Right? Then okay, let's say this is a vp plus 1, and then there is a vp here, right? Then we can represent this vp plus 1 with this one as a linear combination weight, right? Then how can you represent this one? So vp plus 1 will be the c1 times v1 plus c2 times v2 plus cp times vp, right? And then we say that there is a scalar value c1 through the cp which is not zero, right? Because they are linearly dependent, right? And then where is that? Yeah. And then let's say this is the equation 4, and multiplying both sides of the equation 4 by the matrix A, then we can compute something like this and something like this, right? Then it will be C1 matrix A V1, because the C1 is just the scalar value, right? The CP A VP or N A VP plus 1, right? And we already know the A V1 is equal to lambda 1 V1. Because this was the definition of A1. So we can represent this equation as something like this, and this. Okay. And let's say this is the equation 5. And multiplying both sides of the equation 4 by the lambda p plus 1, we want to remove this part, right? And subtracting the result from 5, then we can make a C1 bracket lambda 1 minus lambda p plus 1 v1 blah 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 and 0, because we eliminate this and this one by subtracting. Okay, so and we already know the v1 through the vr are linearly independent, because the vp plus 1 was one is the first index that can be generated with a linear combination. So v1 and vr are linearly independent. So the weight in this one, let's say this is equation 6. Weight in the 6 are for 0, right? Because this is the definition of the linear independent. So it means that this term should be 0, right? So how can we make this term as a 0? So first possibility is the lambda 1 is equal to lambda p plus 1, or c1 is equal to 0, right? But first of all, we cannot say the lambda 1 is equal to lambda p plus 1. Why? Because the lambda was the distinct eigenvalues, right? It should not be 0. So in this case, c1 should be 0, or cp should be 0, right? So in this case, ci is equal to 0 for I is equal to 1 third of p. So for every possible ci should be 0. But this equation 4 says that the vp plus 1 is equal to 0 vector, right? So where's that? So in this case, when ci is equal to 0, then every term will be the 0, so p plus 1 should be 0. So which is not possible. Why? Because the vp plus 1 is the eigenvectors, so it should not be the 0 vector. It will be the non-zero vector. So in this case, the v1 through the vr cannot be linearly dependent, so because it's impossible. So we can say that this statement is not true. So we finally argue that the v1 through the vr, the set of the v1 through the vr is linearly independent, not linearly dependent. So this set cannot be linearly dependent, therefore must linearly independent. Okay. So we proved this theorem. So if we go back to the definition of the theorem, okay, so we can say that, so if we have the different eigenvalues, then we can find out the eigenvectors according to the corresponding to the each eigenvalues, then those kinds of vector should be linearly independent. So this is very important property. So in other words, for the arbitrary matrix A, then we can find out the several kinds of the eigenvalues, eigenvectors that helps to analyze the transformation A. Interestingly, those kinds of vectors are linearly independent. So it's very important property. So which will be used in the our next lectures to understand these properties further. So let's see the next week. Thank you.